Good evening, and thank you all for coming. Thanks for folks online for joining us. Today's about Colorspaces Demystified. And so there are a lot of Colorspaces. They have a lot of different uses. I think we've all used at least one of them, right? Every cell phone, every picture we've looked at is in a Colorspace. And today we're going to talk about how Colorspaces record data, how to convert between them, what they're used for, and no pun intended, the whole gamut. All right, pun intended. So what's a color space? A color space is the language used to communicate colors. And like languages, some are best at saying things than others. They require translation from one to another. And some things just can't be said well in one, but can be said in another. So in a nutshell, that's what we're going to be talking about today. So what is a color space? A color space is really three values used to record a color, and those three values can be in RGB. They can be a luma color difference space. It can be in perceptual, like hue, chroma, saturation, hue, chroma, and lightness. It can be in a subtractive space, like cyan, magenta, yellow, and black. So there's many ways to describe a color space. It's just 3 channels. So let's start with the most familiar color space of all, sRGB. Every pixel you're looking at in this presentation is recorded in sRGB. Every picture you ever taken with your cell phone, camera, anything else is recorded in sRGB. So what's there to know? Every pixel gets a value of 0 to 255. Done. Well, color space is a little more depth than that. There's a lot of things you have to know in addition to that 0 to 255. So there's more to know than just 0 to 255 for red, green, and blue. For example, sRGB is output referred. And what that means is it doesn't record the color of a scene. It records how you want it to look. We need to know, we have these values 0 to 255. What is the relationship between a value of 128 and how bright is a pixel? If I go from value 30 to value 60, does the output light double? Does it half? What's the relationship with that? So we need to know some sort of relationship between pixel code value and pixel brightness. sRGB records values in red, green, and blue. But exactly which green? I mean, this whole area here is green. This could be considered green. This could be green. This could be green. Exactly what green? So we need to specify when we perceive a color, it needs to be in the context of a white point. And we're going to talk about what a white point is. And then finally, what are the viewing conditions? Because in order to, when you decide a pixel value for sRGB space, you're deciding how is that going to look to an observer. And to understand what looks to observer, you have to understand under what conditions looking at it under. Is it a very bright room? Is it outdoors? Is it a dark room? What are the assumptions? So it got a lot more complicated than just 0 to 55. So let's dig into each one of those in more detail. First, we talked about sRGB being output referred. Again, that means it describes how it looks. So if it's not output referred, what's input referred? Input referred is a color space which records the actual colors from a scene. An example of that would be a digital camera, a scanner, a flatbed scanner, or a film scanner, or even a colorimeter can measure directly into a color space. Examples of that are camera raw, XYZ, which we'll talk, and LAB, which we'll talk about later. An output color space would be like sRGB we're talking about right now. Things like a computer monitor, a TV, a printer, those are all examples of output devices where you'd look at color spaces like sRGB, Adobe RGB, CMYK. Those are all examples of output color spaces. A digital camera is a good model for this to represent both. In a digital camera, we can store both kinds of images. We can store raw images, which are input referred. And then after processing an ISP in the camera, there's a rendering process, which also produces an sRGB image, which is output referred. Now, you'd expect that there to be a relationship between the input and output, but not necessarily. Here's an image right here taken. And when that picture was taken, it was probably about 50,000 lux outside. And I'm really sure that the light you're looking at in this display right now is not hitting you at 50,000 lux. So when you have an image that transfers from an input referred space to an output referred space, it'll most likely differ in white point, luminance level, and spectral content. We're going to talk about more of that later. Chromaticities, this is the color of those RGBs. And the RGBs for sRGB are defined to be an exact match to the colors of the phosphors of a reference monitor. And the color of the phosphors are up here. And here's the blue, here's the green. Look at that red. That's really when you're watching an old color TV and just the red gun is running. That's the spectra that you're seeing. Today's monitors have got a much cleaner look. Here's an example of an LCD, which is probably more like what you're looking at right now. And these represent your RGB. Now, on this monitor up here, it turns out that the RGB values in an sRGB were designed to display directly on that monitor without any processing, no color transforms, straight to the monitor. In today's displays, they actually have a bigger gamut than sRGB, which means that you have to do a transform on the sRGB data to display it, but you also can get much better colors. But remember, it's an out-defined color space, so the goal is to make it look perfect on here. It's up to this display to make it look like this display. The color space sRGB uses red, green, blue primaries, and that uses what we call an additive color model. These three corners of the triangle represent the red, green, and blue values. And being an additive color space, anything that's inside this triangle is called the gamut, and anything inside this triangle can be reproduced using these three colors. For example, this yellow right here is going to be halfway between the green and the red, but add no blue. Cyan, for example, or I'm sorry, magenta, for example, is going to be somewhere here between red and blue. So this is a color model, and all the colors we can reproduce are all done by adding a positive value of R, G, and B. Let's talk about white point. So colors are interpreted in the context of a white point. And if you look to the left here, you'll see strawberries. What color do those strawberries look? They look red. Yeah, kind of red. And depending how good your monitor is and your conditions, if it's a nice dark room, that's almost kind of a yellowish kind of color. The folks at home, hopefully you're seeing this in a darker surround. Well, it turns out that the color of the flower and the color of the strawberries are exactly R equals G equals B. They're perfectly gray. So the way you interpret color is in the context of a larger white point. Let me give you another example. Here's a spectral reflectance of an object. And you can see that it reflects very little light in the blue side of the spectrum, but a lot of light on the red side of the spectrum. And as you'd expect, that color is orange. Here's another color. It's perfectly flat all the way across, which of course was going to be a gray. The light reflected that you observe is the light that's reflected from a light source. Some is absorbed, and it ends up being the product of this times this gives you what you see. And so here's the spectral emittance from this product. If we take this gray and illuminate it with a tungsten light instead of D65, of course, it's going to be a much warmer light. And we take the product of these two, we get this result. If you look, this result and this result are exactly the same. Yet we observe that to be orange and that to be gray. And the reason we do that is because our visual systems normalize out the color of the illuminant when we look at a color. And we know that to be true because if it wasn't true, if you went into a room with a tungsten light, everything would look orange, right? It would be like a camera without a white balance. So the white point is necessary to interpret colors because without it, we don't have a reference by which to decide what the color is. So white point is an integral part of a color space. So the white point for an input referred color space is the color of the illuminant. The white point for an output referred color space is the color, whatever the color is of the triad of R equals G equals B. The monitors that we use have a white point. sRGB has a white point of D65, which is, of course, the color outside on a nice sunny day. which is a combination of blue sky and sunlight. And the reason that was picked was, remember this ugly red phosphor? Well, it turns out he's not really good at putting out a lot of light compared to blue and green. So if you make the color temperature so you allow more blue than red, you can make a brighter image with a weak red. So the reason that we use D65 for our white point on sRGB is because the red phosphors on monitors just weren't that beefy. D50 was common use for a reference viewing white point for prints and other things, and that's closest to equal energy. And that would be this, if you can see this orange line right here, that's the spectrum of a D50 compared to the blue line here, which is the spectrum of a D65. So next was the transfer function. That's the relationship between how much light comes out for a given code value. And the monitor physics says, as you linearly increase the voltage, you're going to get an increasing amount of light that comes out. So in order to get the right throughput, we need to precondition the data like this and apply this, it's called a gamma curve, to the data represented by this function, which is really, this approximates down to be eventually a slope limited x to the 1 over 2.2, almost a square root function. And this relationship here, it turns out to be, as Charles Poynton calls in his book, an amazing coincidence, because gamma 2.2 is really close to human visual system, which has a gamma of about 3. And we're going to see that function in a bit. But you may have heard someone say in the past that the reason for the monitor response is the sRGB encoding is because it mimics human vision. Well, no, it mimics a CRT voltage transfer function. It just is convenient that comes out close to human vision. So, I mean, how often you get lucky like that? And another really nice convenient thing is that with this encoding, we can encode almost 16 bits of dynamic range in an 8-bit container, because it turns out that the photon shot noise masks the quantization noise. And this is a very convenient method of encoding large dynamic range with a small number of bits and with almost no lost information content. And for more on that, go see my talk on camera myths, misunderstanding of misstatements, or the HDR talk. I'm going to put a quick commercial here. So I'm part of a member of the Rochester Image Science and Technology group here, and we have a channel on YouTube, and this video will be displayed on the channel on YouTube. And also there you'll find a number of other talks from me and other people and past speakers. So if you don't catch everything that I'm saying here, I'm going to go through rather quickly. If you want to see other talks from other speakers in the past, that's where you'll find them. So do a search in YouTube under IS&T Rochester chapter, and I think you'll find them there. So here's a really important point I want to make, because it's so transparent that you almost forget that it's happening. When we're looking at an image in real life, if the light doubles, the amount of light that hits our eye doubles. When we store this in sRGB, we put on this gamma encoding. And then we store, so the image on our computer is this. And you can see that the highlights are compressed, the shadows are lifted. And so that gives this image kind of looks like this. But we never see this image, because every time we go to display this data, we're not displaying it by reading code values off a screen. We're displaying it by putting it colors on a screen. To put it on a screen, it goes through this nonlinearity. And so every time we try to look at this, we don't see this. We see this after this has been applied, which restores it to this. So on the monitor, we see this. In the scene, we see this. And it's really easy to forget that this is what's actually stored on the computer. So when you go to do mathematical operations on it, color transfer on it, and whatever else, you think you're doing it on data in this form, but it's really this form. And that's an important point to make as we talk about later the applications of what color spaces to do what operations in. Finally, the viewing conditions. sRGB is defined for a monitor with a peak luminance level of 80 candelas per meter squared, or 80 nits. Probably your displays at home are much more like 300 nits. Here's the white point D65. We talked about that. The ambient luminance level. So we're sitting here in a conference room. The lights are on. I'm guessing it's a couple hundred lux in here. If we were viewing this properly, it would be 64 lux, which is a pretty dark room. But it would have to be pretty dark to see things well at 80 nits. And if you've ever been in an environment that had a high-end, highly calibrated monitor, you turn the thing on, you calibrate it, you look at it, and you go, you got to be kidding me. It is very dark. Turns out the spec also includes a typical in-viewing environment. And notice in that case, it says 200 lux, which is a little more like our conditions here, and maybe those for the folks watching online. So that's the reference viewing condition for sRGB. So we covered a lot of ground here, but we've got through our first color space. And just to recap, so the elements of a color space has three primaries. Each primary needs to be defined exactly what its chromaticities are. So what exactly are the coordinates of the R, G, and B as a white point. It has a transfer function, which is relationship with linear luminance. And we need to know if it's input or output referred. So those are the basic elements. And with those under our belt, we can go cruising through the landscape of color spaces, knowing these are just the only four things we need to know. So let's look at the next adjacent color space. And these are color spaces for TV. And I got two here, Rec 709, which is for HDTV, and Rec 601, which is for standard definition TV, if you remember way back then. Comparing, we just talked about sRGB. sRGB and 709 share the same white points and chromaticities. The only difference between the two is the tone scale function. And the 709 has a gamma of 2.0 instead of 2.2. And the reason for that is computers are expected to be used in an environment where the light levels are relatively higher. TVs are typically used in living rooms where the light levels are lower. And because of that, it uses slightly less brighter, slightly less contrastier display. Looking back at the old days of 601, which is again standard definition TV, it shares the same transfer function as the 709, but what it differs by is the chromaticities. And if you look at this chart here, see the SMPTEC. I didn't make up the name. It's very close. It's just slightly shifted. Interesting little point here I just want to cover is look at the size of the gamut for NTSC. So the original color space for broadcast TV. It's huge compared to what we have today. So why did we leave such a huge color space with a huge gamut? The answer is it had two problems. One, the displays were really dim, and the second was the phosphors had a high persistence. So that caused a lot of blurring in the images. Next, let's talk about high dynamic range TV, or HDR TV. I got to change that slide. HDR TV. So an HDR TV, and you've probably seen them, on for sale. You've seen the standards HDR10, which is the bottom of the HDRs. There's HDR10 Plus, which is pretty much a Samsung only. There's Dolby Vision, which is a proprietary one. And then there's another thing called hybrid block gamma. So let's go through those. All of these use the same color gamut, which is this Rec 2020. Look at the Rec 2020. It's huge. It's really big. It's much bigger than sRGB. And now the thing to know about this is, remember I showed earlier the chromaticities, the spectral response of a typical LCD monitor. They're much better behaved, and you have a much greater gamut than you have for sRGB. So a typical monitor has a gamut or a color space bigger than sRGB. So sRGB is holding us back. Well, they made sure that we weren't held back for Rec 2020. To get Rec 2020, you can't get that with a monitor that we can buy today. They do make, if you've got a little extra money, laser projectors where it's the chromaticity of a single monochromatic light source, where you can get Rec 2020 kind of color spaces. But at least in this case, since the displays are bigger than sRGB, they're smaller than Rec 2020, but no longer are we limited by the specification. Now we're limited by the hardware you buy. So it gives you a reason to go out every couple of years and buy a better TV. So let's go through these different color spaces. Remember, we have we have the tone scale, we have the chromaticities. So let's go through them. Of course, these are all still output referred. The tone scale is still like the BT709, which is the sRGB tone scale. The white point is still D65. But it turns out these have an extra feature here. And the extra feature is not only can they get brighter, but they're also stream adaptive. And what that means is these parameters I just gave you are programmable in the stream. So if you have a Batman movie and it has that kind of color look to it, you can say the white point of this isn't D65, it's something else. And so you can specify that per stream. When you go to HDR10, the value added is that you can change that anywhere in the stream. You can change it every frame. You can have one scene that has one set of color space parameters, and the next scene has another set of color set parameters. Dolby Vision ups the bar and says your TV has got a light sensor on the front of it, which measures the ambient light in the room, and it responds to makes the TV color changes in response to the light in the room. So the more you pay, the more you get. And here's the max nits, the brightness levels supported by each one, and the bit depths, which I'm not going to go through one by one, but you can see them there. And the last one is hybrid log gamma, which is a concept of a tone scale, which starts out, it's backward compatible. It starts out as a gamma curve, and then they tack on a log section to it on the end to extend the dynamic range. And that has wide support from what I've looked at, but I haven't seen displays that advertise that. So that's high dynamic range TV. Let's round out our output referred color spaces to talk about a whole group of these. Now, these are color spaces which are generally used creatively, photography, color editing, that kind of thing, where you want to describe how it looks on the output, but you want to describe it in something bigger than sRGB. So let's go through the list here. sRGB, we talked about that in its specs. Adobe RGB, you can see, is a little bigger here. It's in the yellow. And it covers 52% of all possible colors, and it handles a higher light level. It has a somewhat of a lower gamma, and that's been around forever, for especially users of Photoshop. Apple came out with their own, of course, color space, and that has a slightly larger still gamut, and it covers more of the color space. DxO wide gamut is something relatively new. Its color space is defined by 3 monochromatic lasers, which gives you even a larger gamut. And my Kodak friends will appreciate ProPhoto RGB, which we know of as ROM, and it uses a color gamut with a non-realizable or virtual chromaticities. So in order to cover, I mean, this color space doesn't fit well inside of a triangle. And so if you can go outside the triangle, you can get more values. So ProPhoto is the one that we used in Kodak internally for our image processing. And at the time, the researchers came up with this color space after doing an analysis of doing a set of color transforms. In what space can you do color transforms with a minimal amount of hue shifts? So that's the Kodak approach back in the day. So we're going to shift gears. We talked about output color spaces. Let's go to input referred color spaces. The most common input referred color space that I can think of is camera raw, right? Anyone who shot a camera raw, let's go through this list of features or properties it has. It obviously is an input referred color space. The primaries are camera specific. Here are some primaries of different kinds of cameras. I have these are old, but a Canon 5D Mark II, an iPhone, and a Nikon, and they're bluish, they're greenish, they're reddish. So the color space primaries are camera specific. The white point is scene dependent. Here's a scene with a very high white point, somewhere, I don't know, 9,000-ish or something. Here's a scene with a very low white point, I'm not going to guess, but I will guess 2000, something low. So it's still a color space. It has its white points. It has its chromaticities. The scene input space will have a black level, which is typically not zero, but it's up a few percent from black. The white in the camera is going to be some code value. It's camera specific, and also can be ISO specific. But when you have all these values defined, you can actually use that to infer what the colors in the scene colorimetrically. Another thing I want to say is, remember how we talked about on the output side, you can only add colors. You can't subtract them. So then that limits your gamut to the inside of the triangle. In camera space, you can digitally take these numbers and subtract them to create a larger gamut. Kodak made a camera, maybe others, that had subtractive primaries. So the camera had cyan, magenta, yellow. And even with those, we could produce all the colors we needed to, because we could subtract one from another to represent colors outside that triangle. It added noise and had some other problems, but it demonstrated that's possible. So just keep in mind that in an input color space, the primaries, it's not an additive system. You can subtract and create colors beyond the gamut of the three primaries.
Slide previous to this one.
Yes.
What is wrong about saying that the white point?
You're right. The white point, the question was, what's wrong saying the white point is luminant dependent instead of scene dependent? You're absolutely right. In my mind, I was thinking that the illuminant is scene dependent.
Makes sense to me.
Good clarification. So I want to make a point here about the process of rendering or converting from an input to an output. We take it, and the digital camera is a nice model to do that with because it does both. So when we take a picture, first step we do is a white balance. And a white balance makes the image so that from the camera sensitivities, we normalize it so that red equals green equals blue for neutrals in the scene. And if you remember, the white point for an output display is the white point of R equals G equals B. After you go CFA interpolation and we create our full color image, the next step is a color correction. And the color correction is a transform from the camera primaries to your output space primaries. So that's when you would convert from camera RGB to sRGB, for example. Also in that step is where we apply a rendering curve and the gamma correction. So that gets applied in this step, and we compress it and we save it. So that's the conversion from a camera raw RGB to an sRGB. But let's just zoom in on one important point. Here's A and here's B, and for those who are familiar for looking at Macbeth color checkers, and depending upon your viewing environment, which of those two looks more accurate and which of those two looks better?
Right.
So the one on the right, B, is exactly the code values defined by X-Rite for what their color checker should be. The one on the left is gone through a rendering. And what I mean by rendering here is, by design, the input color space and the output color space almost never match. And in this particular example, I would say that A is probably preferred over B. A looks a little snappier. A probably matches your, this looks a little muted, a little off. And so why does this look more accurate when that's really the more accurate representation? And the answer is, when you're viewing this image, you're viewing this image in the presence of viewing flare. So what that means is light from the room is bouncing off the monitor and hitting your eye, which is making the blacks lifted. And to compensate for that, we need the blacks a little blacker. Another thing is, typically when you take a picture of an image, it's under higher light conditions and you're viewing the image. I mean, remember that reference monitor for sRGB was 80 nits. That's pretty dark. And the way the eye works is when the scene is dimmer, your perception of color goes down. So the chroma goes down when luminance goes down. And so to compensate for the fact that the viewing conditions are typically dimmer than the taking conditions, to compensate for that, you need that little contrast boost. So these curves here represent the green is your typical gamma. The blue is the gamma that was applied to convert this to this. And the red is the shape of the tone scale to give that little boost. And that's any digital camera you have is, unless you set it on, I think there's an accurate, sometimes there's a color look called accurate. If you set it for that, it'll get close. If you don't set it for that, if you have it for portrait or landscape or scenic or normal, it'll always add this color boost for those reasons. And further on top of that, I'm sure everyone here, everyone out in internet land who's taken a picture has edited it, or anyone who's ever seen a well-polished picture on the internet or anywhere else will notice that the pictures look snappy and contrasty and beautiful, and someone spent a long time breaking that connection between the input color space, which is accurate color measurement, to the output color space of how it looks. So I just want to reinforce the fact that an output, sometimes we like to think, oh, I have an sRGB image. I can turn that back into an input color space and know what the colors are in the scene. Well, no, we try really hard to make that not true. And you try really hard every time you edit an image to make sure that's not true. So let's talk about some other input referred color spaces. sYCC, which my friend Bruce here used to work on, is scanned film. And they convert that scanned film and try to take out the filmness of it and turn it into as though it came from a scene. And it's stored using CCI, so the 601, the standard definition primaries, and it's stored as a Luma chroma image. We'll get more of that later. White point D65. And it has a neat thing. It uses unclipped RGB, which we're going to talk about later. And it measures up to 200% reflectance. RIM is a Kodak invention, and it uses the same. Here's the primaries of our RIM. So remember ROM we talked about earlier? Well, RIM and ROM. ROM is output metric. RIM is input metric. What was the other M? RIMM.
Right?
No, it was reference input metric. Medium metric. Okay. There was an ERIM, which was our HDR encoding color space, and that handled everything from 0.1% reflectance up to 316,000% reflectance, which covered pretty much anything I ever worried about. And there are some HDR formats out there as well, and their transfer function's linear. They're in units of luminance, so if you look at the code values from that, they'll be in candelas per meter squared, for example. And I'm not going to dig into those because there's a whole bunch of them, and time doesn't permit to dig into them, but they're out there. I'm sorry.
Why is that there? Yeah,
so the question is, it can hear is why is this here? And I just want to show the relationship of the we're going to get to this a little later, but this diagram here, this chromaticity diagram, is showing the perimeter represents monochromatic light. For example, a laser. So these are the purest colors you can have, and then the white point is in the middle, and then we have you've seen the RGs and Bs around here, and the gamut that these things encompass. This surface colors is to say that in real life you don't run into many monochromatic reflective sources. Right. And so these huge gamut color spaces are fun and all, but are they really needed? And so the reason for showing this locus of colors is just to show, what kind of things you normally run into, as opposed to what are the physical limits. Thanks for asking that. And you're right. There's something called Pointer's gamut, which I had an earlier slide and I forgot to mention. So thanks. Okay, so now we're going to talk about another color space, an input-related color space. We talked about camera raw having these spectral responses. Well, wouldn't it be fun if we had a spectral response that was related somehow to human vision? And here's a set of such spectral responses, and they're called color matching functions. And the primaries are defined by these color matching functions here. The white point, again, is seed dependent. The transfer function, it's linear with light, and it's a input seam referred color space, and it's scaled such that black is 0, 100% diffuse reflector is 100. So we're going to talk about these curves here, but first we're going to do a 5-minute color science primer. Don't read the subtitle. And the purpose for talking about this is, if we look at these pictures here, this is taken under tungsten, 600 lux, a low color temperature. This is taken outdoors, and the sun is shining down on this, so it's about 5,500 Kelvin, certainly much brighter. And then this one's a luminous light blue sky, and it's a much higher still color temperature, higher light level. And yet, under these conditions, and never mind that's a photograph, you as a human under each of these conditions would view this color target to look identical under all three, more or less identical. And we need a system which we can use to relate color in all these different environments and have a consistent color. And so even though these are very different brightnesses, very different color levels, we maintain a hue, a lightness, and a chroma. And how do we do that? And it's the image science that holds it all together. So I'm going to do a little segue for just 5 minutes or more, and explain how these blocks work together. So it goes back to the eye, and the eye, as you know, probably remember, has got 4 kinds of sensors. It's got scotopic vision, which is by the rods. Then we have 3 flavors of cones. They're called short, medium, and long. I know they kind of want to call them blue, green, and red, but they're called short, medium, and long. And the interesting thing is, in our fovea, in the center of our field of view, is the only place we have these. And if you look really close, you'll find there's almost no short or blue receptors. Very few. Less than 1% of all cones are the blue or short. And in the very center of your field of view, there's none. So overall, we have, or at least in the center 1%, more than half are what I want to call the red ones. Almost 40% are the green ones, and the rest are the blue ones. So that's a distribution. And looking at these color shapes, it's important to point out, you can kind of see two things going on here. One thing is we've got this lonely blue, and so we have a color perception which kind of lives on this. Is it the blue or is it this cluster axis? And then we have another color system that says, are we trying to tease out a signal between red and green? I mean, look how very close together these are. There's a very common type of color blindness where these two curves line up on top of each other or very close to each other. And when that happens, red-green discrimination becomes impossible. So, and the reason why is just look how darn close those two are. So that's a lovely color system, but it's not very practical for doing math. So back in the 1930s, they said, we need to take, I'm sorry, I'm not there yet. Sorry, I'm going to slide off. They did an experiment where they gave somebody a monochromatic light source in blue, a monochromatic light source in green, and a monochromatic light source in red. And they said, okay, here's a reference color, and we're going to take this reference color and we're going to change it with monochromatic light all through the spectrum of colors from a red to green to blue. And we're going to give somebody these 3 colors and some sliders, little amplifiers, to change how much light you can see for each one. And so then for the red, they would adjust, I just have some red energy. That's supposed to change color. When you get closer to the green, of course, you start adding some green to match the user-controlled section to the reference section. And when you get to here, I remember in an additive color system, you could only add colors inside the gamut or inside the boundaries by the 3 chromaticities. So when you get outside of this, you can't match the colors anymore, right? You can't add a negative red, which is what you'd need to do. So what they did is they said, okay, we'll allow you to put a red light on the reference side, and the amount of red you add here, we'll just call that a negative red. And so you can see as we go through this part of the color space, we needed to add a negative value, which gives us this minus lobe. And of course, you had to add blue to match the colors along this part of the curve. So those are the color responses, and these are called the CIE RGB. That was found to be a very impractical set of color matching functions. And so, oh, there we go. Now it turns to green and blue. All right, I should have studied up on this. So they decided not to use those and decided to change into something else, into these set of color functions. And why these? Well, for one, they're all positive, which makes the math a little easier. Another one is it was really darn convenient to make one of the colors be this green line. And what this green line is the photopic efficiency function. And that function measures the eye response to how intense does a light look at each of the wavelengths. So in other words, at around 540, somewhere in there, you need very little light. And as you go out to here, you need twice as much power to get the same perception of lightness, and a quarter as much power, and so on. When you get to the very end here, you need a lot of energy to get the same response for brightness. So that was fixed. That had to be that for Y. The other requirement was had to be all positive values, and the third requirement is that the output X, Y, Z functions have to be a linear combination of the input, so a weighted sum. I'm going to go past this. We have an example coming up that makes it easier. And the other thing is, so think of these as like camera responses. Think of these as being, instead of the RGB curves, here are our new curves and represent the eye response. And when you multiply the incoming light times the reflectance of an object, then the way our new camera sees it, it's basically the same as multiplying these all up and integrating. And these integrals need to be normalized by this K factor. And this K factor, just to decode it here, is to basically say I take 100% diffuse reflector and I normalize it so that it turns out to be a value of 100. In some systems, you'll see this is normalized to actually 1. So you got to watch out for that. So the idea of normalizing it is, remember that slide before which showed the color checker under the different light levels? Well, by normalizing it, it says that a 100% diffuse reflector has value 100, regardless if it's under a very bright environment of 100,000 lux on a ski slope on a sunny day, or if it's in your basement underneath a tungsten light. So it normalizes out the light level. So all along here, I've been showing you this horseshoe diagram. I never said where it came from. There's another color space called, oh, I forgot, I got to go back one here. So that defines, the integral of these things define our XYZ, and the XYZ is a color space called CIEXYZ, and they're also called tri-stimulus values. There's another very closely related color space to that, and that's what makes up these color diagrams we've been talking about and creates the horseshoe plot, is we take the X and a little x, little y, and it's basically computed by taking the capital X, capital XYZ, sum this ratio. And that's used to create this. So basically, this takes out the intensity of the color and just maps the chromaticities, and these are the chromaticity plots we've been looking at. And a thing to note is the gamut of this, of course, is the coordinates of the system, and it includes some space where it's physically impossible to create a color. So again, this locus along here are single wavelength emitters, and you can't, if you're emitting less than a single wavelength, you're dark. So I heard someone say once that, well, once technology gets good enough, we're going to be able to make layout here. No, that's not going to happen. That's mathematically impossible. Sometimes you'll see that this encoding little x, little y, capital Y, is used for HDR, in which case the value of y isn't 0 or 1, but actually is in units of candelas per meter squared. So we went through this calculus math here, but I want to bring it home and make it into something real. So let's just take an example. See this patch in the color checker? It's called the blue flower. And here's the spectral reflectance of it, as you'd expect. It has more blue, it has almost no green, and a little bit of red. So here's the question to ask. Here's the spectral reflectance of this. Say we put it under a uniform light source and it has the same color temperature, so we don't have to worry about that math, just to simplify things. And here's another light source. It's a laser with some energy around 420, basically the three ones used in that color experiment. Can we recreate this color using this spectra? So here's the spectra of this color. Does that look exactly the same as that? Well, how would we know? Well, let's go through and compute the X, Y, and Z values. So here's the spectrum right here, is this spectrum right here. Here's our Y bar color matching function, Y bar, Z bar. We take the product of those, we get this answer, we integrate it all up, and we get a number 220. And do the same thing over here. We take our little spikes here, multiply that times the color matching function, measure the area underneath all these curves, and we get this 27, 19.4, and 36.3. So as we compare them, remember cap Y is the brightness. Here's the brightness of 19.6. In this case, the brightness 19.4, pretty darn close. The X value 22, 21.7, Z value 36.9, 36.3. So it turns out that this XYZ pretty much equals this XYZ. These two stimuli will create the exact same color to less than half a J&D. So here we have now we have a color system, which allows us to say we have very different spectra, but we have a way of matching colors from one set of spectra to another set of spectra, completely unrelated. And just because we get the same XYZs, we can say they have the same color. And that's the glue that holds this whole system together. I'm not going to spend a lot of time on this because it's a little deep, but I just want to make the point. So when we measure an XYZ, remember, it has its own white point. So you have to record the XYZ of the white point so you know how to interpret the XYZs you collected, just like we did with sRGB, and instead it had a white point of D65, and we showed that earlier. Say you want to change that white point from something like a tungsten thing to a D50 thing. Well, you can do that. What's interesting, and what this math does, and I'll boil it low down in a hurry, is you take the primaries of XYZ, you convert it back to cones, you do a white balance operation like you do on a digital camera and normalize it out by the white point of your destination, and then you convert it back to XYZ. So it's really like doing a camera, and when you think about a camera color balance, it's also done in the sensor primaries. And so we're kind of doing the same thing that we do in a digital camera, but we're doing it in cone primaries. Next color space we're going to talk about is CIELAB, which is based on XYZ. And we take the XYZs, and it's basically a luma color difference color space. And this is the exchange space used for color management and ICC profiles. It's used very widely, and it has a transfer function of gamma 3. Its white point is scene dependent, but if you don't see a white point associated with it, you can assume it's D50. The chromaticities are going to be the same as the chromaticities of XYZ, because that's what it's computed from. It's a luma color difference space where one axis is a blue-yellow and the other axis is a red-green. Does that sound familiar? We talked about that a little while ago. And let's just look at this. Here's the calculation for it. And if you remember this plot from earlier, XYZ was normalized for lightness. Remember, we measured the integral for a 100% diffuse reflector and normalized it so that it was independent of light level. Well, the LEB calculation also divides out the, see this YN, XN, that is the XYZ of the white point. So what we're really saying is we have some color we're looking at, and we're going to divide this out to get this. So basically, it's doing what we knew happens in our vision system mathematically. It's normalizing out the illuminant from the spectral emittance, which leaves us with the color of the object. There's limits to this, though. First of all, obviously, I want to say this. This is probably really obvious. This only works for color vision. Right? If you're out in the dark and you're using your scotopic vision system, none of these color transforms predicts color well. And as you get towards the edge of that space, it also doesn't predict color well. And it's because the normalizing for light level and normalizing for white point works up to a point because we adapt only up to a point. If we were using the XYZ or an LAB to predict the colors of this, it would normalize out the image so that it would look like it was perfectly exposed. And of course, when I was standing there, it didn't look like it was midday. And it would also perfectly take out the colors and make it so that if there's any neutral, here's, I think, a gray sweatshirt. That would be gray and not reddish. So keep in mind when using these color systems that it does normalize out for light level and color, but only up to a point. And another place where it doesn't work well is you've ever been in a weird situation where the illuminant, you can adapt to illuminance along the black body radiation curve. So that section of light from, reddish to bluish. Have you ever been in a situation, for example, where the light's been really green or magenta or some color that's off that axis? And your mind just hurts because everything looks really odd. That's another place where we don't adapt. And that'd be another place where XYZ or LAB would not predict the color of an object. One more color space to talk about, again, an input referred color space, one used for color modeling, one used, I think, less often. I don't run it very often. And it's called CIELUV. It's easier to compute than the LAB. It has its users. I can't speak too much detail on that. So let's shift gears. And we talked about input color spaces and output color spaces. We're going to go back to input color spaces because we introduced this idea in LAB of going from an RGB-based color space to a Luma color different color space. And there are some flavors of that same model that exist in the output color space worth visiting. And those would be a set of video referred color spaces. And these all are pretty much the same animal. There's a bit of an ambiguity about the letter style that represents them. A Luma Chroma color space, it takes an RGB image and it divides it into a Luma image. Remember old black and white TV? And chroma difference images. And where this came from is going back in TV. We all had black and white TVs. Well, some of us had black and white TVs. And then color came, and they wanted to have a system that was backward compatible. And so it would still modulate the luminance information, but they had the way to add the color information, which is the color burst signal, independent from the Luma signal, so that the TV broadcast would still work. So everybody who bought a color TV could see color, and everyone who had a black and white TV could still see their black and white programming. It turns out to be a very efficient color space because our eyes are very sensitive to luminance modulation and less so to chroma. And so the bandwidth of the color differences can be reduced without much loss of image quality. The basic makeup of them is you start with an RGB color space, and you start with different RGBs depending upon which flavor. So Blu-ray and HD formatted video is computed from the BT709 color space. DVDs, SD format video is from the BT601, and JPEGs are encoded typically in this color space, and they come from sRGB. And the basic recipe is you compute a Luma by some spec for that color space, and then you compute these color differences, which is going to be blue minus the Luma and red minus the Luma with some scaling factor, offset, because this is going to be a signed number, right? If you subtract these two, you offset this, and so it biases it back up, so 0 is at 128, which means you end up with a color between value between 0 and 255. And this A and B value and your Luma weights are dependent upon which color space you're starting with and what the spec is. This letter salad of YUV, YCC, YIQ, YCBCR, you don't really know what it is by its name, and you really need to chase back to where it comes from. And it's a trust yet verify. It's a hint. It's not a very good naming convention. So don't trust the name. You have to chase it back. And the way to chase it back is really see where is it coming from and see what is the specification for Blu-ray, right? Or what is the specification for a DVD. There's something you have to be familiar with is this BT601, which is an early standard video DVD format. Sometimes it uses a luma value that goes from 16 to 235, and sometimes it uses a luma value from 0 to 255. And here's an example of an original. And the error you can make is it was encoded in the studio limited luma format, and you decode it full, or it's fully decoded studio. In one case, it comes out less contrasty with lifted blacks. In the other case, it comes out too contrasty. It's not a huge difference, but in the engineering world, we always want to be perfect. So be aware of that, and it's another trust yet verify. And I can't tell you how many times that has burned me and probably others in the room. So here's a fun color space. It's called sYCC, and it's basically the same as sRGB that we talked about earlier, but it's converted to this YCC, and it's called unclipped RGB. So why is that important? Well, it's a fun color space because this is the same trick that was used in photo YCC, which predated it by a decade. Yeah. The idea is when you convert from your camera RGB to sRGB, you're going to have some numbers which are going to be outside the sRGB gamut. Suppose you didn't clip the numbers which are less than 0 and greater than 255, but you let them exist as a signed number bigger than an 8-bit unsigned value. And then you go through this calculation here. This space can be made bigger than sRGB. And so allowing negative sRGB values to exist in this space allows you to expand the gamut. In fact, the gamut is big enough that you can extend into this non-realizable space of colors. So it's a huge color space, and it doesn't take up any extra space. It's still an 8-bit unsigned number with a large gamut. Kodak jumped on that bandwagon for, I think, about 3 or 4 cameras in the consumer space. Epson tried to market this as a feature so that you could get a match between an Epson camera and an Epson printer, which meant you got really much better greens, was really the big space where you noticed it. Today, I don't hear about it anymore. The next color space, these are perceptual color spaces, where you can take an image and convert it into percepts like hue, saturation, and intensity, or chroma and lightness, or intensity can be intensity, lightness, or value. And the difference depends upon, for example, value is the brightest color of the RGB triplet. Intensity is the average of the 3, and lightness is the max minus min. Why we need all these different ones, I don't know. These are handy when you want to look at a percept, but keep in mind that this is a buyer beware. These are converted from RGB. Well, as we said earlier, RGB is an unambiguous color space. When you say RGB, everyone knows exactly what you're talking about in terms of tone scale, chromaticity, white point. Of course, I'm being facetious. But at least it comes up with color channels which correlate to these percepts, even if not exactly the same one. If you're really interested in these values, I would really recommend using the LAB values in computing chroma and hue from those spaces. But these are available and they're out there, so I thought it was worthy to describe them. So now let's talk about color spaces or image operations. We've talked about this, what color spaces are the properties of, what are the components of them. Now let's talk about what's the best color space to do different kinds of operations. And at this point, I'd like to quote a Kodak researcher who said, feel free to do anything you want to an image, but if you can't explain the physical basis of what you're doing, they're just making stuff up. and that's Ted Gindel. So the point is, you can take any color space and you can do any kind of operation. It will change the look of the image. But if you're trying to do something very specific, let's give an example. An exposure shift, a flare adjustment, and a white balance gain. Mathematically, they're a linear space transform, and a flare is a subtract from an image. A white balance is a channel specific gain, and an exposure shift is a non-channel specific gain. Okay, so this is the physics, and the math says this is how you apply these transforms. What normally happens, though, if you've used pretty much any imaging operation, if you have an image here that's underexposed, and here's an example of an image that's underexposed by 4 stops. If I were to take that image and do a histogram stretch in my favorite image application, Photoshop, or something of the like, to restore the lightness level, I'd multiply it by a number that's not 16, and you'll get a picture like this. If I were to take this very same image, convert it to a linear space, again, remember it's an approximation, right? Because we already learned that the sRGB, if you bring it back to a linear space, is going to have some transforms which may not exactly preserve its linearity. And then multiplied it by 16 and re-rendered it, I get this result. If I took the capture again at the right light level, I would get this. If I were to take this image, go into a raw editor, and add a 16x gain, and then render it, I get this. So let's look at the results here. These two are pretty gosh darn identical. This is not a bad approximation of this. And this one is very contrast. You see how the blacks and whites are, the black is much darker, the white is lighter, and see how the colors are much more saturated. So it felt like I did an exposure shift, but on top of that, I added contrast and I added saturation boost. So if you're going to do an exposure shift, the right place to do it is in the linear domain, not in the gamma space. Let's look at this same operation as a white balance. Here's an image captured under tungsten light, but I applied, I don't remember if it was a D50 or a D65 white balance correction. So the end of the result is it's very yellow, right? If I take this into Photoshop and if I do normalize on that, you'll see that we get red over here and we get blue over here because we're trying to do a linear operation on nonlinear space. If I convert it to linear, I get a pretty well a white balanced image. Again, some loss in colors in the transformation going back and forth. And if I do it in RAW, this is exactly the same as doing it in the camera natively. Here's the right answer. So this is an example of it's common practice to do these kinds of transforms on images in the wrong space. Linear space would be the right answer, and gamma space is not. This is true, by the way. I talked about sRGB. We talked about other color spaces, Adobe RGB, ProPhoto, and all these other ones. And it's not an sRGB thing. It's the fact because it's in linear space, not the chromaticity. So the same problem you'd get if you did these same adjustments in those other output referred color spaces. It's because of the gamma curve. There's another operation too. Any linear space operation, for example, you've heard of diffraction correction. Basically, it says if I take a picture with a very small aperture, I'm going to get diffraction from the small aperture, which causes a blurring. And if I want to sharpen that back to as though I was using a larger aperture, I can calculate the kernel that I would need, and I can convolve that kernel over the image and sharpen the image. And that effect happened in a linear space. And so the correction has to happen in linear space. And so the basic rule of thumb is whatever space it's broken is the space you fix it. And by the way, gamma is almost never that space. So what's the best color space for computer vision? Well, the best color space for computer vision is the one that's already used to train the existing model. If you do have the freedom to pick any one, then the right answer is the color space which encodes and restores as much information about the scene as possible, which means it has to be input referred. it should be white balanced unless the illuminant is a predictor for what you're trying to figure out. Very large gamut and large dynamic range. And the other point to make is don't assume that human vision is the reference to be emulated. Our human visual systems work great for the things that we do, and we've evolved as a species and done pretty darn well. But our color vision system is, picking ripe berries from unripe berries. It's being a good predator and avoid being prey. Computer vision tasks may be none of those. And so the color space you want to use and the system you want to use is the one that emulates and best matches the discrimination task at hand. Suppose you're computing an image from scratch. Say you're making a test target. You're creating a simulated scene. You're trying to demonstrate some numerical expression, right? What color space am I in? Well, the answer is you're in whatever color space you want to be. You're in charge. But don't assume that you create an image buffer, you calculate your image, and you go to display it and say, I've done it. Because as soon as you do that, remember, before you even see it, it's going to go through this nonlinearity we saw before. So here's an example of pure green, pure red, pure blue, and then the blending of all the colors in between. And this was done, just as I said, computing those mixtures. But then I had to add a gamma curve to that because I knew that was going to be followed by this. Here's a step wedge, equally spaced shades of gray. Again, I computed that and applied the gamma curve to that. Well, what happens if I just say, well, the heck with that. I'm just going to display what's right in my buffer. You get this, which is clearly not equally spaced step wedges, and you get this, which may look more aesthetically interesting, but it doesn't represent a linear mixture of the colors throughout the gamut. So just keep that in mind that when you compute your own from scratch, the color space is the one you pick. But again, remember that the default is going to be a gamma because it's going to, the computer on is most likely going to assume that you're working in an sRGB color space and display it as such. How to convert between color spaces. I don't want to spend a lot of time on this. We're probably deep into the talk here. But remember the elements of a color space. We have three primaries with a white point and a transfer function, and you may be in a luma chroma space. So the first thing to do is undo the luma chroma. It's to remove the nonlinearity because remember, changing white points and primaries need to be done in a linear domain. And then you compute a set of matrices, which I'm not going to go through. We're short of time. Then you reapply the transfer function. So what I'm going to say instead is, see this little QR code. Bruce Lindblom is out a website. This is a link to that website. He has all the color transformations for the color spaces that you most likely to run into. You've pre-computed all these matrices. I recommend go there. No, have you? Okay. Yeah, the question was, has anyone ever met Bruce Lindblom in person?
And I don't know a single person that's ever met him.
Okay.
He knows his stuff.
Absolutely. He's a great resource. So here's a set of color spaces by function. I'm not going to go through this all right now, but that's sort of divided up into the sort of things we've talked about today, different categories. So finally, what have we talked about today? Color space is three attributes. It has a type, whether it's input or output referred. It has chromaticities, which are the colors of each of the RGs and Bs. It has a white point, and it has a transfer function, and it may or may not be represented as an RGB or a luma color difference space. The process of converting from input referred to output referred is called rendering, and it typically does not preserve color. It's intentionally different for a number of reasons. You can reproduce a color using entirely different spectra, white point and luminance up to a point. Remember that picture of by the campfire, right? As long as you're using normal light levels and normal luminance, we can go from, if you remember that continuous spectra of the blue flower to a very non-discontinuous spectra and get the same perception of color. XYZ is normalized for light level, and LAB is further normalized for white point. And we saw that with the orange patch. Remember, we saw the orange patch could result in the same spectral emittance, yet be perceived as different colors based upon the white point, and XYZ is normalized for light level. We talked about that. sRGB and other gamma output color spaces are great containers, and sRG specifically, it's great because it's display ready. If you have a reference monitor, you throw those the signals right at the monitor. It needs no transform. The gamma exactly matches the inverse function of the CRT. The chromaticities of the color space exactly match the colors emitted by the phosphors. It's really fun because it has a response close to perceptual. So it does feel like the gamma in it is like a human color response. And the fact that it can code large amounts of information virtually lossless is very nice. But the takeaway here is, but it doesn't model any photographic phenomenology, and it's the wrong space to correct most photographic issues. I just want to give a shout out to Bruce Lindblom again. He has a great website, and also Charles Poynton, his books here, Digital Video and Digital Video Interfaces, has been my reference for this and throughout my image science career. They're great books and they're great references. And congratulations, you made it to the end. Are there any questions? Bruce, do you want to see it in the chat? Or are there any questions from online?
Oh, yes. So wavelength from sRG.
I was trying to derive wavelength from an sRGB image. The question is, can you derive wavelength from an sRGB image? If you look back to the talk by Susan Farnan at RIT, they do they have a talk which is about archival imaging, and by using two sets of captures with a different color filter, they can basically get six primaries, and with those 6 primaries, they can go back and build an estimate of the spectral reflectance. So that's done with 6 primaries. With 3. I think you can come up with an answer, and you can make some assumptions. You can say the spectral response is always positive. That's a good guess. You can say in nature, there are no sharp transitions in spectra, right? They tend to be fairly continuous. And so you can apply that constraint, and that'll get you somewhere. Whether it's close enough is probably up to your own criteria. So is it a fool's errand? I think it would be fun. I think you'd get an answer. The people who have done this found they can do something useful with 6. And I'm guessing the reason they went to 6 and not 3 is because it's probably not good enough for their uses.
Oh, yeah, and Peter confirms more succinctly.
Very good. Well, thank you all for listening. I appreciate you all coming out tonight and giving a listen. And for the folks online, thanks for dialing in.
All right. Thank you. Here is your official certificate.
Yay! Thank you.